All right. Good evening, everyone. I want to walk through a demonstration of how we might approach teasing apart simple effects within a mixed repeated measures ANOVA design. In this screencast, we're going to go through and work with the 3x4 repeated measure ANOVA with the ordered means. We had gone through the omnibus effects within this data set and detected a within by between interaction. What we're going to do is go down through and take a look and talk about how you might go about teasing apart and sort of identifying or qualifying that interaction. Recall that what we have here in these data are measuring depressive symptoms among individuals seeking inpatient treatment at intake, at 2 weeks, at 4 weeks, and 6 weeks, and then we're splitting this up by program 1, 2, and 3. These are just different treatment programs. The question here is whether or not we see different patterns of response in terms of mean depression symptoms across these repeated measures assessments by these different treatment groups. So again, pulling this up and taking a look here. Also have the data set up here. Want to take a look real quick. I'll go through a formal screening of this eventually, but just to go through and take a look and start to try and tease a couple things apart in terms of these characteristics of the data in thinking about how we're going to approach this in terms of qualifying that interaction. So if we go through and sort cases by program, again, what this is going to do is it's going to split the file by the different program and just look at our descriptive statistics. We're going to see all of our values are within range, which is good. And then if we're looking at our indices of distribution, our skew and kurtosis values, looks like we're maybe a little kurtotic at week 6 in program 1. Things are looking okay in program 2. Pretty kurtotic in program 3 by the time we hit week 6. But again, we've got fairly large cell size. Well, not fairly. We've got really large cell sizes for between groups design. So that's going to help us out quite a bit. We might then go through and take a look at the graphical distributions here, turning the split file off and just running these analyses by program. Again, we're familiar with all the descriptive means here, but if we go in through taking a look at our histograms, things are looking okay for program 1, 2, and program 1, 2, and 3 at intake. As we get to week 2, we start to see more skew here. As we go to week 4, increasing skew. Some people hang out here at the end, and then by the time we get to week 6, we're seeing one person in program 1 is an outlier. We're also seeing an outlier here in program 2 at week 6, outliers here in program 3 at week 6, and so in terms of our distribution, we're not too worried, because remember the assumption with our means-based analyses is that we have normality in the distribution of sample distribution of sample means. With samples over 100, the distribution of sample means for these data are going to get pretty normal pretty quick. But we do have some outlying values here by the time we get to week 6 across these scores. But also sort of recognizing that we conveniently have a extreme value for each one of our groups. So it's not just we have like one group where we might have an outlier pulling things out. We also have over 100 people in each cell. So probably we could probably tolerate these in terms of not having too much of an impact on our overall means. But again, this is something we'll tease apart a little bit more as we go through in the screening demonstration. So just want to get some characteristics of this. Also, if we go through, take a look at our variances. If we were to run Fmax, again, we're wanting to look at between and within subjects' effects. Again, I'll walk through that when we hit the screening. Our Fmax ratios aren't too bad, suggesting that there's no huge difficulties in terms of our variance assumptions within and between. We look at here and we see that our design is not perfectly balanced, but we've got large cells for each one of these, but we do have unequal sample sizes to at least some extent here. And then if we go down through and take a look at our Levine's test for our between subjects effects, remember, think of this as a one-way ANOVA design, looking at differences across treatment groups at intake, at 2 weeks, at 4 weeks, at 6 weeks. We're seeing that we're pretty good when we start, but as we start to continue on through treatment, by the time we hit week 6, we've actually sort of have some evidence of violation of homogeneity of variance. And so some things to think about as we're plotting or trying to figure out how we're going to start to tease apart this within by between interaction, right? So again, remember, we see a main effective assessment suggesting that collapsing across treatment groups, we see a different pattern or changes in at least one of these means relative to the next, or relative to the others. We didn't see a between subjects effect, suggesting that we're not seeing overall over the course of treatment differences in across treatment programs, at least collapsing across all time points, which we talked about. It may not be a really meaningful test. But what we're really interested in here is this assessment by program interaction. Remember, if we look at our greenhouse geyser correction here, we see that we're easily meeting criteria for statistical significance here, suggesting that treatment group is moderating pattern of means across repeated measures assessments, such that something different is going on in there, or the pattern changes in one group relative to the next, somewhere in there. But we've got a lot of means, a lot of groups. If we go down through and we take a look at our overall graph of our marginal means, we see that people are clients are responding at least somewhat similar in form, right? But our interaction tells us that by definition there's some statistical difference in the pattern of these means over the course of time. What we need to do is think about how we're going to go through and start teasing apart this interaction in a meaningful way, where we're not using up a bunch of power, wasting a bunch of things on frivolous pairwise tests or things along those lines. So in thinking about our approach here, some things we might want to keep in mind in terms of our overall approach here. So we've got clear reductions. Again, we've got over 100 people within each one of these cells, and a clear effect of time. We can look at this and eyeball it, and if we have any basic knowledge of statistics, we're going to recognize that we've got clear impact. I mean, we could go through and test whether or not these individual points are different within each individual group, but that's going to be sort of gratuitous. It's fairly clear that with samples over 100, we're going to get big effects here, right? So maybe what we want to do, and again, assuming that we didn't have any a priori hypotheses about how we were going to approach this, given that we're looking at treatment response across 3 different treatment groups, maybe what we could do is say, okay, well, we want to go through and we want to make sure that everybody, or we know that everybody's improving over the course of intervention, but maybe what we want to do is start to qualify sort of the magnitude of that effect. Okay, if we were to say, okay, for some random person in treatment 1, 2, or 3, what are the treatment gains that we should expect within the population based on the data that we have here? And so what I would probably suggest is maybe looking at pre to post treatment change within each treatment group but not focus so much on the statistical test, because we already know that's going to be reliable. It doesn't make sense to go through and test things that we already know are statistically significant, but make a focus on effect sizes. Okay, maybe we're going to go through and we're going to say, all right, let's go through and qualify sort of average difference and create a confidence interval around mean difference from pre to post. That might be helpful for other researchers and clinicians to say, okay, how much of an effect should I expect? How much of a symptom reduction should I expect in individuals participating in these treatments, both in terms of raw change in BDI scores and maybe a range of values, upper lower limit for some sort of standardized effect. So that's effect size. Those are confidence intervals. We don't. I'm not going to worry about correcting for that necessarily. But then we also have between subjects effects that we could look at. Now, we've got 1, 2, 3, 4 different time points at which we could run between subjects contrasts across average group depression levels. But I don't know if we have a good reason to go through and test each and every one of those. What may be a more interesting way to try and qualify this interaction is maybe we run a test at between groups tests at time 1 at intake to see whether or not people are coming in at a relatively similar symptom level. Again, we see these means aren't on top of one another, but what we might want to do is see whether or not we see systematic differences or have evidence of systematic differences across individuals at intake, and then maybe do the same thing down here at discharge or at 6-week treatment, right? We could go through, and so this approach isn't really taking into account, at least when we're probing things, the full repeated measures design, because we're kind of ignoring some stuff in here. But unless we have specific hypotheses or are expecting sort of one group to change more rapidly from intake to week 2 or across these different time points, unless we have some good reason to test those, that might just be sort of running tests or run tests, difficult to determine whether or not that's going to be a useful thing to do. So for our approach here, what I'm going to propose is that because we're not coming in with good and clear hypotheses on the front end, what we might want to do is, because we see clear symptom reductions from intake to 6-week in all groups, what we're going to do is calculate within subjects effect sizes and 95% confidence intervals within each group to try and give us some sense of the magnitude of change we should expect in the population over the course of treatment. So that's going to be our within subjects piece. And then what we're going to do is, for our between subjects difference, go through, and take a look at group differences at intake and 6-week assessment. Okay. Now, what this means, if we go through and take a look, if we've got 3 means to compare here, 3 means to compare here, that means at each time point, at intake and discharge, or at intake and 6 weeks, we've got, we can compare program 1 and program 2, program 1 and program 3, program 2 and program 3. So we've got 3 possible pairwise effects we can test here, and same thing, 3 possible pairwise tests we can test here, which gives us a total of 6 pairwise tests. These are post hoc tests that we're going to run, and we're just doing some exploratory stuff to see whether or not there's any differences between these groups. So we're probably going to want to do something to account for the number of tests that we're running, correct for these specific contrasts in a way that's going to help make sure that our type 1 error isn't too terribly inflated. Now, some things to think about in terms of how we might go about and correct these things. We had talked about in class, and Howell goes through and talks about this, some more elaborate ways of going through and running specific contrasts using your mean squared error from your overall omnibus effect to go through and start teasing apart individual contrasts and things. But my problem with that is, and this is reflected in some of Howell's thinking in the text, I'm not confident that we're 100% on all of our assumptions here. Our sample is not perfectly balanced, which isn't a formal assumption, but there's some differences here. We have large sample size, and so we're not too worried about this, but some problems or some discrepancy in terms of our overall sample. We do have some issues with the distribution again, but we have some large sample sizes that are probably going to not cause those outliers to have too much of an effect. Our F max isn't bad, but again, we've got some evidence of violations of homogeneity variance, at least within our between groups. Now, this is going to be a highly powered test, just given the number of people we have in the sample, but suggesting that things are starting to get more variable as time passes, which is often what we see within these types of treatment studies. And so, while we could maybe get crazy and start pulling specific contrasts using our mean squared error, I think we're going to be okay just going through and using just standard pairwise tests here without capitalizing on the pooled variance from our overall ANOVA table, and also sort of our high degrees of freedom associated with that mean squared error. This is going to produce a more conservative test than we might otherwise, but given sort of possible violations, and then the fact that we also have over 100 people within each cell, I'm pretty comfortable sort of disregarding sort of the more elaborate approaches to pulling contrast with the components here, and just running pairwise tests to get at some of the things that are going on. So we've got 6 pairwise or 6 between subjects contrasts that we're going to be taking a look at now. In terms of ways to go about controlling, we could run a Bonferroni, but again, Bonferroni is not really for exploratory analyses. We're running 6 tests. That's starting to get pretty heavy in terms of correction. Same thing for Dunn-Sidak here. You'll see for correcting for 6 tests, Bonferroni alpha level is 0.008. For Dunn-Sidak, it's 0.009. So those are always going to be fairly similar. Another thing I could think about is using modified Tukey. Okay. Remember we had talked about this last semester, kind of taking Tukey and bending it to our will. This actually turns out to be kind of advantageous if we set our Tukey for our Tukey. If we set r equal to 4, right? We say in an otherwise situation where we would be looking at 4 different means, what this is going to do is it's going to control for 6 comparisons, which is actually the same number of comparisons that we're looking to control for, so that's useful. Now, in terms of degrees of freedom for our Tukey, a couple of options. Traditionally, with Tukey, we would go through and pull our degrees of freedom error from our overall omnibus table here. But again, hesitant to do that given some of the things that we had talked about. If I'm wanting to be fairly conservative, what I might do in this case is set my degrees of freedom to 222. What that's going to do is that's going to correspond to the lowest number of degrees of freedom between sort of my smallest contrast. That's going to be comparing sample 2 and sample 3. 101 plus 123 is 120 or 224. Subtract 2, that's going to give us 222 degrees of freedom. And so maybe what I want to do is compare all of my contrasts, at least between means at time at intake and at 6 weeks, using sort of our most conservative degrees of freedom. So if we set r to 4, degrees of freedom equal to 222, we're going to end up with a Tukey Q, or a critical Q value of 3.67. Now, where am I getting that? Actually, we can just pull this up if we go critical Tukey value. Here we go. Yeah. So if we go down here to this data or to this website here, Fisher R to Z. Okay, we've got R is 4. Here they're calling it K. 202 degrees of freedom. Calculate that. Gives us a Q value, a critical Q value of 3.67. And so we've got 3.67 here, but because I'm going to be running just some regular old t-tests, between subjects t-tests here, in probing this out, what we can do is we can take that Q value, convert it over to a critical T. Remember, this is just our Tukey critical value divided by the square root of 2 gives us a critical T value, corresponds to a T value of 2.6. Okay, now, and again, if this is what we're going to do, what we would do, any pairwise test that we conduct, what we would do in before we'd count this as statistically reliable, we would go through and compare our test statistic against a critical value of 2.6. If it exceeds that, we'd say, yes, this is reliable with our modified Tukey correction. If it's not, we would say, well, we don't have sufficient evidence to claim an effect here given the correction to our test. And so, not that you would do this, but if you were interested in how this test statistic compares to maybe a correction with the Bonferroni or the Dunsetic, we can also go here, and what is our 2.6? If we want to look at what a test statistic of 2.6 would look like with 222 degrees of freedom, that's going to give us a p-value of about 0.010. Okay, so we can see that our modified Tukey test is giving us a little more power than Dunsetic, which is giving us a little more power than Bonferroni, which is pretty much what we would expect. Okay, so we've got our game plan. Going to run, just calculate some confidence intervals and within subjects effect sizes and confidence intervals for our within subjects contrast to see what's going on there, and then what we're going to do is take a step back and look at some pairwise tests at intake to see if our groups are different when they start out, and then at 6 weeks to see if we can detect differences when people finish up. Okay, so we're going down. First thing we're going to do, we're going to sort first split file by program. Okay, if we go through, I guess we can just do this here. If we go through data, split file, and we're going to organize output by our program variable. Okay, and we say OK. What this is going to do, is it's going to split our file up, and so if any analyses we run at this time is going to run unique analyses for program 1, program 2, program 3. So if we go analyze, compare means, paired sample t-tests, we're going to compare our intake scores to our 6-week scores, and then we're going to hit OK. All right, and we see this is the output we get. We can just click back over to our handout. Same stuff is on here. We see, and again, purpose here is not to run the statistical test, because the statistical test for program 1, program 2, and program 3, these are massive t-tests with 100 degrees of freedom, 140 degrees of freedom. It's kind of gratuitous if we were to go say, oh, we're going to run each one of these. But what we might want to do is go through and calculate our effect sizes and corresponding confidence intervals for each one of these to try and get a sense for the magnitude of change we would expect in this population should they be participating in program 1, program 2, or program 3. So program 1, first thing we're going to look at here, and this is one of the reasons we just ran this in SPSS, it just gives this to us automatically so we don't have to crank through a bunch of hand calculations. We see that we get a mean symptom reduction of little over 15 points. So 15-point reduction in BDI scores with upper and lower limits in the population, somewhere between 13 and 17 points. Okay. Again, if we go up here and take a look, this is program 1. We're seeing somewhere between in the population, we would expect somewhere between 13 and 17-point reduction in BDI scores based on people completing 6 weeks of program 1. Okay. Other thing we can do is maybe we want to calculate a standardized effect. So if you're a clinician, you work with a BDI, you say, oh, 15-point reduction in the BDI is pretty big, right? But maybe we want to standardize that given variability within this sample. And so what we can do is pull up our trusty calculator that we put together last semester. So you keep this around, it's helpful. And what we can do then is very quickly go through, punch in our mean to start, 24.70, down to 9.32, standard deviation, 12.586, 9.582. Get that right. All right. Standard deviation of difference, going to pull that there. Okay, so this is, all right, so we've got mean at time 1, time 2, standard deviation at time 1 and time 2. These are going to give us different metrics of effect. Standard deviation of the difference, this is actually the one that we're going to use because what we want to do is calculate confidence intervals around our point estimate of effect. You can punch this in if you want. This is for the D paired, although it's not really relevant to much of anything else. 141 is our sample, and then we need our non-centrality parameters. Okay, this is another reason to go through and run these formal tests within SPSS, not because we're terribly interested in whether or not we're meeting statistical significance, because we know that they are, but what we need, remember, is this test statistic here and the corresponding degrees of freedom to get non-centrality parameters around our within subjects effect. So if we pull up our Steiger calculator here, T, 95% confidence intervals, what we're going to do is we're going to say 15.116 with 140 degrees of freedom for this group. Compute. This is going to give us our upper and lower bounds for our confidence, or for our effect size, so 12.460 and 17.741, we'll call it. All right, and so what we see is for program 1, we're seeing about 1 3/10 of a standard deviation reduction in symptoms from intake to 6 weeks, with a range of plausible value for this effect within the population, expecting anywhere from 1 to 1.5 standard deviation reduction in depression scores over the course of this treatment. Right now, again, here's D average, delta, D paired, different metrics for this within subject effect. But again, what we're going to be doing is we're going to be pulling the D difference here using our standard deviation of the difference score as our standardizer. Again, remember, because this is the standard, this is the variance estimate that goes into the calculation of our test statistic. And if we're using this test statistic to calculate the bounds of our, to derive the bounds of our effect size, we need to standardize our point estimate or effect using the same variance estimate that went into here. Now, so the question is the standard deviation of our difference scores systematically smaller than variability at time 1 or time 2, concerned that we might overestimate our effect? As with most treatment types of studies, we're saying that it's actually pretty comparable. It's a little bit smaller than the variability that we get at baseline, but it's sort of larger than the variability we see at the end here. If we were to average it, it's probably going to be higher than that. And if we actually go through, we see that our D difference using standard deviation of the difference score as our standardizer is smaller relative to our pooled variance across these two, and so we're not worried that this is an inflated standardized effect, right? So what we end up with, if we go through and pop up here, start looking at our within group change, we have a mean symptom reduction of a little over 15 points on the BDI, with upper and lower limits in the population expected to be somewhere between reductions of 13 to 17.5 points. In terms of our standardized effect, we're seeing about a 1 3/10 standard deviation reduction over the course of the treatment for individuals in Program 1, with expected values in the population of individuals receiving this treatment running somewhere between a little over a standard deviation to about 1.5 standard deviation reduction. So if we're looking at Program 1, pretty impressive, right? But let's go through and see what's going on in Program 2. Okay, if we go down and look at our data for Program 2, basically, we're just going to do the same thing for Program 2. We're going through, if we look at just the raw reduction and corresponding confidence interval, we've got mean reduction of 19.3, right, which is suggesting some greater reduction, at least in terms of absolute value relative to Program 2, and then our 95% confidence interval around the point estimate of this mean change, ranging anywhere from close to 17 to 22 point reduction in the population of individuals receiving treatment in Program 2. Okay, what we can then do is go through, run the same effect sizes, going through, plugging that into here in our calculator, and if we do that, we'll see that for Program 2, slightly larger absolute value in terms of magnitude of just raw symptom reduction, 19.4 relative to 15.4, but also if we look at our confidence intervals, very little overlap here, right? So our upper limit for Program 1 is a reduction of 17.4 points. Here in Program 2, our lower bound for our population effect, or our population mean we would expect in population, is about 17. So again, if you think about that Cumming and Fitch article where we're looking at comparison of our confidence intervals, looking like, at least based on our mean reduction, that we may have some evidence of Program 2 sort of looking maybe a little bit more effective than Program 1. Still clear reductions across both of these, but maybe Program 2 is doing a little bit better than Program 1. Not sure yet, right? If we look at our standardized effect, we get a standardizing using the mean or the standard deviation of the different scores, slightly larger effect size. We've got about a 1.5 standard deviation decrease in Program 2 from pre to post, or from intake to 6 weeks, with a interval around our effect size running from about 1.2 standard deviations to 1 3/4 standard deviations. Okay, so more overlap in terms of our effect sizes than it is in our raw change in means here, but maybe could put together an argument for possibly somewhat better effects in Program 2. Same thing if we go down to Program 3. See a 20-point reduction, at least in terms of absolute magnitude within this sample. Confidence intervals around our point estimate running somewhere from an 18-point reduction to 22.5-point reduction about. So if we go through and we run our effect sizes here, we get sort of 1.66, so close to 1.7 standard deviation reduction from intake to week 6, with interval around that point estimate running from about 1.4 to close to 2 standard deviation reduction. Here, boundary for our interval doesn't even overlap with Program 3. So we can probably conclude that in terms of absolute magnitude, we're seeing a stronger reduction or a stronger treatment effect in program 3 relative to program 1, at least sort of eyeballing our confidence intervals. And then in terms of our effect sizes here, not a whole lot of overlap between our upper and lower bounds. So again, this is just estimation, sort of trying to draw general conclusions about what's going on with these data. But as I'm looking at this, as we go through and we just contrast just overall treatment reduction from intake to post-treatment, would suggest that maybe our just raw means or just absolute reduction, suggesting maybe program 2 and 3 might have some marginally larger reductions, or at least if we're talking about 3, larger reductions relative to program 1. A little bit different if we're looking at our effect sizes. Effect sizes look like 1 and 2 are fairly similar, 2 and 3 relatively similar, but in terms of our effect size, it's starting to look like we have something that looks like a reasonable difference in terms of our standardized reduction in depression scores from intake to week 6 across program 3 and 1. Okay, and if we go through and we go back up and we take a look, this is kind of consistent with what we're seeing here. In terms of absolute reductions, greatest reduction in 3, 2 and 1. We're seeing 2 start out maybe a little bit higher in terms of absolute magnitude, end up at the same place as 1, but in overall terms of absolute magnitude and then effect, looks like 3 is probably doing the best, at least within subjects change. Okay, so that gives us a sense, or we can at least start to talk about, draw some inferences about what may be going on within this interaction, and how these means are maybe changing differently across repeated measures assessments, at least based on comparisons of time 1 and time 2. Now, we could go through and test each one of these individually, but then burden is on us to say exactly why that's important and what it means. I don't know that I'm sort of up for doing that, not just because it would make this example much longer, but conceptually, unless there's something meaningful that's going on between weeks 1 or intake and week 2, or something meaningful that's different across these programs that's going on in group from week 2 to week 4, wanting to think carefully about whether or not these are all meaningful differences and important contrasts to run. Okay, but what we talked about before, remember wanting to go through and do some between subjects tests to take a look and see what's going on, to see if we can see differences. Do people reasonably start out similarly? We've got some clear differences, at least in terms of absolute value. These dots aren't all falling on top of one another, but what we might want to do is run some tests to see, do we have a reliable difference or evidence to start teasing apart, to see if we need to start to tease apart any differences here, and then the same thing at week 6. So we can say this, did you get a general sense if people are starting out kind of a similar spot, and then are they ending up, do we see differences in where people end up? That's, you already know what's going to happen there. But is the difference we see at week 6 between groups 1 and 2 and 4, is that large enough to claim that group 3 is systematically ending treatment lower than our other 2 treatment programs? Okay, so what we're going to do, so these are our within subjects contrasts, right? What we're going to do now is we're going to go through, and I'm not going to go through and do it in SPSS because you can sort of see right here. We're going to turn off our split file because we're going to run everything together. And what we're going to do first, and actually I will run this just to show, because we're not on the page here. But what I'm going to do first, before I start going through and running a ton of tests, what I might want to do, split file is off now. Okay, what I might want to do first, close out of that, is go through and at time 1, see if I even have, at least at the omnibus level, evidence for something that would warrant jumping in and making all our pairwise comparisons. And so what people will sometimes do in this case is say, okay, what I'm going to do is I'm just going to run, look at differences across treatment program at intake and at 6 weeks. Okay, what I'm going to do first, before I even jump into the pairwise test, is I'm going to go through and take a look and see if I have evidence within an omnibus test to even jump forward and even move into our pairwise test. Because if I don't see a clear effect of group in these one-way ANOVAs, that kind of alleviates me of having to go through and start trying to tease this stuff apart. So we're going to run a one-way ANOVA across groups at intake and at 6 weeks. We're not going to run any contrasts because we're just interested in the omnibus test here. Post hoc. Now we went through and talked about how we're going to go through and run our post hoc tests. And you might say, well, why don't I just pull my post hoc tests from SPSS? Well, if you think about why that's going to, how many tests is it going to correct for, or what's the correction for the test going to be at each time point? With 3 means it's going to correct even if we select Tukey here. What SPSS is going to do is it's going to give us a correction for 3 tests at time 1 and 3 tests at week 6, which is going to be less of a correction than we already decided that we wanted for our 6 tests, right? SPSS is just going to correct for 3 and going to correct for 3, which is going to be a lower critical value than what we want for the whole thing, right? So this is why you have to be smart and think about what you're doing and plan appropriately with this. So what we will ask for, we want descriptive statistics, homogeneity of variance tests, and then we're going to ask for our Welch. Remember, our Welch is a corrected omnibus test given evidence of violations of homogeneity of variance. So I'm going to hit continue, I'm going to hit OK. And what we've got here is our descriptives across treatment groups at intake, our descriptives for treatment groups across treatment groups at 6 weeks. If we go down through, take a look at our Levine's test, again similar to what we saw in the overall mixed design. Really, it looks like there's variability in scores are pretty similar across individuals at intake, but by the time we get to 6 weeks 6 weeks out, we're getting some pretty clear evidence that things that our variability in our BDI scores across treatment groups is starting to look somewhat different. Again, if we sort of just to get a general sense of what this would look like if we go back through and run this, scroll all the way down just so we can look at our box and whisker plot across treatment group at week 6. This is where we're starting to see within our, within our homogeneity of variance tests here. And so this is saying that by the time we get to week 6, variability in BDI scores across groups is starting to get a little bit, is starting to get different. We're seeing systematic differences that we would expect in the population. And if we scroll down and sort of jump back into some of our screening things, we're starting to see that here, right? For group 3, less variability. Group 1, more variability. Now, some of this may be due to these outlying values to some extent, but what it's suggesting is that maybe we want to run a correction for homogeneity of variance, at least in the data as we have them. So if we go down through and take a look at our one-way ANOVA at intake, we're just right on the cusp of a reliable group effect at intake. This is marginal. Well, it's not, I mean, it's 0.05, and we're not really correcting for these omnibus tests. You could make a decision to say, and if this was clearly not reliable, right? If this was 0.4 or something like that, what we might say, or even if it was 07 or something, we might say, you know what, we're running a bunch of tests. It doesn't make sense to go through and start teasing apart pairwise comparisons here at time 1 if we're not getting a reliable effect of group in our one-way ANOVA that we're running here, right? Now, this is a marginal, so this is right on the cusp. This is right at what we would say is clinically or statistically reliable. So I'm going to go through and do this, but an argument could be made for, given all the tests that we're running, maybe we don't go through and do that, but we will here. Looking by the time we get into week 6, we are seeing that we do have a reliable effect here, suggesting that at least one of these means is different than the rest, which, if we're looking at our graph, it doesn't take much intellect to decide where that's probably going on. But our omnibus test saying, yeah, go ahead, go and run these pairwise effects, worth going through and exploring. Now, the one thing I would note is that we did violate our homogeneity variance assumption for our omnibus effect at 6 weeks depression. So probably what we should be doing is not looking or focusing primarily on this, but because we've got a violation of our homogeneity variance, dropping down to our Welch's test, right? But if we drop down to our Welch's test, we're seeing that we do have evidence of differences across these groups still. Our p-value is actually less than what it was here, so suggesting that, at least for the purposes of this example, what we'll go through is we'll go through and tease apart and look at our pairwise comparisons both at intake and at week 6. Okay? And if we go through and so that's our within group, and so our between groups, right? We're running one-way ANOVA model at intake in 6 weeks. Our F-test at intake is technically statistically reliable, so we're going to go through and proceed with running our individual tests. If it wasn't, though, we'd say omnibus effect wasn't, or omnibus test wasn't reliable. No need to go through and individually formally test each one of these. Now, we're still going to correct for the 6 because that's what we'd planned for. By looking at the graph, we kind of eyeballed it already, so we're going to correct for them. But if in the case of a significant or clearly non-reliable omnibus test, we'd probably just go through and forego this. But we're going to go through and do it because it's right at 0.05. At 6 weeks, we're seeing statistically reliable omnibus effect, but probably what we're going to put more emphasis on the Welch's because we had a violation of homogeneity of variance. But regardless, both of these statistically reliable, and so both at intake and at week 6, going to go through and run our pairwise comparisons. And so remember, with 3 means, we can test group 1 and group 2, group 1 and group 3, 2 and 3. And so what we're going to do is just go through in our t-tests is we're going to go through and we're going to request a t-test comparing program 1 and 2, our variables being BDI 1 and BDI 4. So what we're doing here is if we go analyze, compare means, independent sample t-test, we're going to for at intake use program as our grouping variable, and we're going to look at 1 and 2, continue, paste that, right, so here's our t-test, and then let me just copy this and say we want to do it again. This time though we want to compare 1 and 3, and this time we're going to compare 2 and 3. Okay. oops, and what we should have done here is BDI 4 as well. Okay, going back up just so you can see what this looks like in the in what we would do here is we would say, okay, what we're going to do is we're going to compare program 1 and program 2 at intake and 6 weeks, and if we paste that, this may be redundant, but just so you see what we're doing. So, oops, it's almost 1 in the morning, so I'm sticky on the keys here. All right, 1 in group 3 and 2 and 3. All right, I'm going to sneeze real quick. Or I'm not, that's fine. All right, so here's how we would set up our t-tests to go through. And again, we could go through and ask for post hoc tests, but again, that's not what that's going to do. Is it's going to go through, and if you ask for Tukey, what Tukey is going to do is it's going to go through and pull from the mean squared error in your overall omnibus test, and it's going to correct for 3 contrasts instead of 6. And so what we're going to do, we're just doing this by hand to go through and run it so that we're actually getting the critical or the test statistic that we want, so we can compare it against our value, our critical value that we derived with our modified Tukey for all 6 of the comparisons that we're going to make. And so this is just going to be a more efficient way of going through and doing that. So going through comparison of group 1 and 2 at intake. Go through here. We see we haven't violated our Levine's test, so we're going to go to our equal variance is assumed. We're seeing that we have, if our at alpha level equal 0.05, we would conclude evidence for a reliable difference between group 1 and 2 at intake. But remember, our critical value that we're comparing this again to correct for multiple comparisons is 2.6. We see our t statistic here is 2.39, which does not exceed 2.6. So despite the fact that we would probably identify this as a reliable effect at a per comparison error rate, we're not going to do that here. We're going to say, well, don't have sufficient evidence with our correction to go through and conclude a reliable effect. If we go down through and we take a look at differences between group 2 and 3 at intake, again, no violation of our Levine, so we go to equal variance assumed, but clearly not meeting criteria for statistical reliability in the difference between group 2 and 3, and the same thing between 1 and 3, no violation of Levine's. Going here, no evidence of an effect. And so if we go to, in summary, what's going on at intake, we see 1 versus 2 would be considered statistically reliable at our per comparison error rate, but not after our corrected test. 2 and 3 and 1 and 3 clearly not meeting criteria for statistical significance. And so based on these data with our correction for multiple comparisons, we're going to probably conclude that even though we're seeing some differences in the absolute means, that sort of within the population, not strong evidence for differences across, or we don't have sufficient evidence to claim reliable differences in these populations at time 1, time 2, and time 3, or excuse me, at program 1, 2, and 3, which makes some sense particularly if these people were clients were randomized to treatment groups, right? So other thing we can then do is go through and take a look and see if we have differences at 6 weeks, right? So again, we're getting all this same stuff within SPSS. If we go through and look at our 6-week scores for programs 1 and 2, again, not violating our Levines, and we're clearly not seeing differences there. And again, we know that because those two means are right on top of one another. Okay. If we go down through and look at the comparison of group 2 and 3 at 6 weeks treatment, we're showing we do see a violation of Levine's test here, and so we would go down through and look at our equal variances not assumed, and so we're seeing again what looks like at a per comparison error rate a reliable difference between 2 and 3, but our test statistic here is 2.38, which does not exceed our critical value of 2.6, and so again, close but no cigar. With our correction, we're not going to be able to claim strong evidence of a reliable effect here. And then what we're going to do is we're going to compare groups 1 and group 3. 1 and group 3 at 6 weeks, again, violation of Levine is going to drop down, equal variance is not assumed, and here we're getting a test statistic of 2.7, which does, hooray, exceed our modified critical value of 2.6, and so what we could then do is go in and want to calculate an effect size, want to see what's going on in terms of the magnitude of an effect. So we've got a mean of 9.32 versus 6.42. You're excited I made you guys create these calculators right now, right? 9.582 for standard deviation, 7.689. We've got 141 people in program 1 and 123 in program 2. We'll go through, pop up our calculator here, and we're going to say, all right, now this gets a little bit tricky because we've got two different t-tests that we could calculate here in 2 different degrees of freedom. For the purposes of calculating a confidence interval around our effect size, given that our G value, our pooled variance, is the same variance that's going to be going into the calculation of our uncorrected t, we're going to go through and enter our uncorrected t to get our upper and lower bounds of our non-centrality parameter. Again, wanting things to be, when you're doing this, when you're calculating confidence intervals around a point estimate of effect, because we have to use a test statistic to get the upper and lower bounds for our non-centrality parameter, want to make sure that whatever your test statistic, the variance estimates used to calculate your test statistic, is the same one that was used to calculate your effect size. So even though we use the statistical or the corrected t to make an inference on whether or not we had sufficient evidence to claim a reliable effect for the calculation of our confidence interval around our what ends up being Hedges G, we're going to go through and make sure that we use the uncorrected test here. So 262, 2.682, 262, 95, boom, okay. And so what we do is we can say 0.706 and 4.653. All right. And so what we get is a Hedges G. Again, this is using our pooled variance estimate, which makes sense because we've got different sample sizes and different variance here based on our Levine's test. So we're going to use our Hedges G, confidence interval, lower bound for G, 0.087, upper bound 0.57. And so if we go through and translate that over to our sort of just general write-up, what we end up with, okay, for our between groups, we're seeing things are looking pretty similar at intake, but by the time we get to 6 weeks, we've got reliable effect at our for our omnibus that says, okay, go through and start teasing apart these pairwise. We see that 1 and 2 are almost identical. 2 and 3 are starting to look that way if we hadn't corrected for a bunch of stuff, but we're doing a bunch of exploratory things, so that's reasonable. By the time we get to 1 versus 3, we do have evidence of a reliable effect. Our test statistic exceeds our critical value of 2.60, but we're not seeing a huge effect here. Something that would probably be qualified as a small effect. About by the time we get to 6 weeks 6 weeks into treatment, we're seeing about a third of a standard deviation difference in group 1 versus group 3, corresponding to an effect size with a lower bound of about a tenth of a standard deviation expected in the population, anywhere up to close to over a half a standard deviation. Okay, so all in all, what do we say based on this? How do we go through and say, because this is important, right? We're not just doing this for the hey-ho heck of things and not just running tests to run tests. We want to sort of come up with some conclusion about what's going on based on the combination of our within between subjects contrast. And so remember that with our within group, looks like 3 is outperforming 1 at least, depending on whether or not we're looking at effect sizes or raw means. 1 and 2 looking kind of similar, or maybe sort of getting a little bit of an edge on group 2. And then our effect sizes, everything's looking fairly similar at intake, with some differences noted at 6 weeks, predominantly differences in groups 1 versus 3, with sort of 2 and 3 not quite hitting statistical significance. So maybe what we say, and what might be a short, sort of sweet summary reading of this is, so that we see between group, within subjects contrast, suggesting evidence of greater outcomes in program 1 relative to program 2, program 2 with intermediate effects with our within stuff, but looking moderately favorable to program 1. If we're looking at outcome, where people end, program 1 looking like it's people are doing, or program 3 is doing systematically better than program 1. So the combination of our within between suggests that probably people doing better, sort of at least with comparison to program 1, that program 3 may have better outcomes in terms of reductions in depression, and where people are in the end or ending up at 6 weeks post-treatment, and then maybe program 2 somewhere intermediate within that, with some evidence of more favorable outcomes relative to program 1. Okay, so this was a lot. So to my timer says an hour and 2 minutes. So thank you for sticking with me, but hopefully this is helpful in thinking about how we might go through and start to tease apart within between interaction, some of the considerations we might want to make here. Again, we didn't go through and use some of the classical approaches by pulling out mean squared errors from your overall ANOVA table, but we probably had some violations. Our data sort of are looking kind of tricky in some spaces, probably not enough to say that we are, definitely not enough to say we shouldn't move forward with the analyses, but to the point where we might start worrying about trying to capitalize on elements of the design and things like that. Also, we have over 100 people in each cell. I'm comfortable here breaking back to just pairwise tests and sort of modified corrected values for our post hoc analyses, and sort of not worrying too much about the loss of power here. Again, given that we already have considerable power to start with. And so, again, some ambiguity, but at least I think a reasonable story we can wrap up with these data, which is sort of about the best you can hope for with these types of studies. So hopefully this was helpful. Thanks for sticking with me. Let me know if you have questions as you're working through, and what I'll do is I'll go through and post up, work through the unordered means. We use a little bit different approach there, play around with some contrasts and things. All right, good luck.